begin. I realize that we have about 6 weeks left in the course, or something like that. And so it seems like it's probably a good time to start wrapping up our discussion of two-dimensional systems so that we leave ample time for three-dimensional systems and chaos, and also discrete time systems, iterated maps, and fractals. So those will be the topics for the last bits of the course. But let us just try to polish off some of the phenomena that can occur in two dimensions that we didn't talk about yet. And so we've been discussing limit cycles, closed orbits in general, and the way that they can bifurcate. And up till now, we've pretty much focused on the case of the Hopf bifurcation, where a limit cycle emerges from a spiral, fixed point. But there are these, I mentioned once very briefly that there are three other types of bifurcations that come up frequently, and so I want to start by discussing those, which you can read about in section 8.4 of the book. So refer to these as other bifurcations of periodic orbits. Also, I do have homework to return, homework 5, so don't let me forget at the end. Let's collect those. Well, so the first one to discuss, we have mentioned briefly already, which is the saddle node coalescence of limit cycles. That is where a stable and an unstable cycle collide and annihilate and disappear. So this we saw in this system. It was a system that we used as a model for a subcritical Hopf bifurcation, but we also mentioned that this bifurcation occurred there too. So we could write it as A dot is let's say a control parameter mu r plus r cubed minus r to the fifth. And theta dot is 1 plus a constant b times r squared. So this system, you may remember, had a bifurcation diagram where if we just look at the r equation, so that's a one-dimensional system that decouples. If you look at R, the fixed points of R versus the control parameter mu, we saw that R equals 0 was stable up to some place. In fact, it's mu equals 0. And then there was this backward bending unstable branch, and then becomes stable and goes off like that. And so this bifurcation that's occurring down here is the subcritical Hopf that we discussed in the last lecture. And so remember, these, although these look like fixed points in the phase plane, they would be, well, this fixed point at 0 amplitude is truly a fixed point. That's just the origin. And so, like, say, for a region down here, if mu is, actually, let me comment that there's one other, this is really the bifurcation we're interested in, the one that occurs here, where we've got this unstable branch merging with the stable branch. So let's call that place mu sub s, s for saddle node. And we could calculate, by just studying the properties of this curve, that the r dot curve, that mu s turns out to be -1/4. So that's a little calculation you can do. And that's the place where we're having the saddle node bifurcation of cycles happening there. And so that's the one I want to make sure you get pictorially. So if we look at the phase portrait in the different regimes, let's first look when mu is less than mu s. So if mu is less than mu s, that is, we're somewhere over here, then the only attractor in town is the origin. And so we would have a phase portrait. Well, if we draw the r dot versus r picture, just in the radial direction, we would see something that looks like this. You can show that r dot is strictly negative except at the origin, and it just has some kind of, maybe I should move my label down a little bit. Sorry about that. It looks sort of like this, the cubic. I've drawn it a bit overly flat. It could have a min, a local min, like this. So the flow on the radial direction just goes monotonically to 0, and we have this stable point in the plane. Now going into polar coordinates in the plane, theta dot is not too interesting. Let's just suppose it's monotonically increasing. Then we would spiral in like so. So there's our stable point at the origin. Then, as we increase mu and approach mu s, something interesting happens, which is, so far this was for mu less than mu s. Let me draw the other two pictures. So when mu equals mu s, and when mu is greater than mu s, but let's suppose it's still less than 0. So that the reason for that is I want to have this stable cycle existing up here, say in this region. So in this region, where mu is between mu s and 0, we have a big stable cycle. Something like so. And then we also still have, as you can see, there's two stable objects. There's this stable cycle and a stable fixed point. This has some, whatever this radius is. So that's the big R star on that circle. There's also a stable point here at the origin, and in between there's this limit cycle that's unstable. So there'd be some dashed unstable cycle in here. And we're just flowing around the same direction on both of those. And inside here we would spiral into this fixed point. And we'd also spiral out. If we're outside the dash cycle, you spiral out to that stable cycle, and then from here, stable, you spiral in. So we have coexisting attractors in this region. The system is bistable. And the amazing thing, the new kind of bifurcation, is as we move, say, back this way to mu s, the unstable cycle and the stable cycle collide, as you can see by, sort of moving this way on the picture. These two points come together and collide at that point. So that would give us then this funny object, which I guess we haven't really talked about much, which is a kind of, I don't even know really how to draw it. Maybe I'll just draw, well, I mean, I don't know whether to draw it dashed or solid, because it's a kind of half-stable cycle that is looking in terms of this picture, the R dot picture. Down here, the picture was stable at the origin, and then the cubic, sorry, this fifth degree polynomial has a shape about like what I've drawn in this region that we're talking about, where there's a stable point here, an unstable point there. We go this way, and that way, and that way. So that's our flow here. Now, you can see what's happening as we move, say, this direction, decreasing mu, is that this max is being pulled down, and at some point it will just become tangent to the axis. So we'll have something like this. And when that occurs, then we have this stable, this saddle node bifurcation happening here. This point is still stable, but we now have a half-stable point, stable from the outside. like so. And so that gives us a, I'll just draw it as a solid object, although it's really only half stable. So we're spiraling into it from the outside, but away from it on the inside. All right, so that's the saddle node merger or coalescence of cycles. And it's kind of odd in some ways. I mean, like from the point of view of, suppose you were here at equilibrium and everything was cool, you're happy. Now you start changing the parameter. You wouldn't notice anything as you go. I mean, but what's weird is that this stable or this half-stable object just pops out into existence out of nowhere, seemingly, at large amplitude. Out here already at this amplitude. There was really no hint of it. I mean, one hint, I guess, would be if you were able to detect the flow in the radial direction, you'd see that you were kind of getting almost stuck. In fact, you would be getting stuck at that radius if you came from the outside. So there would be that amount of hint. But if you're just in the neighborhood of the origin, you wouldn't really see anything happening. Anyway, is there any question about this series of pictures? And so one thing I want to do in this lecture is emphasize some of the different scaling laws that occur near these different bifurcations. This is sort of the physicist's way of thinking about things. That is, what are the critical exponents that characterize the different bifurcations? Yes?
If the satellite bifurcation, you start just inside of the periodic orbit, would you still be going to the origin?
Yes. The question was, if you started just inside this periodic orbit, you're talking about this picture, right? Yeah, if you start just inside the periodic orbit, that would be like starting just to the left of that half-stable point. Then you'll just be driven monotonically to the origin, which in the phase plane means you'll spiral in. Right? Your radius will continually decrease. So you just spiral in. Right? Is there another question? No. So, yeah, let me then say that what we're seeing here is that the cycles that are born at mu s, you know, sort of with multiplicity 2 at first, let's keep track of what their frequency is at birth and also what is their amplitude. You know, are they big or small, or are they fast or slow or moderate or whatever? So in this case, the cycles are born sort of fully grown. They're born at an order 1 amplitude. Where when I say order 1, what I mean is I have some small parameter in the problem which refers to my distance from the bifurcation. So here I guess I mean with respect to the small parameter mu minus mu s in absolute value. So when I'm close to mu s, the size of the limit cycle is not comparably small to mu minus mu s. It's in fact just some order 1 number. And also, they are born with order 1 frequency. That is, they're not fast or slow. Because you can see from this theta dot equation that when r is r star, nothing special happens to theta dot. It's just some number. So you're just spinning around at some reasonable frequency and amplitude. So that's a hallmark of this particular bifurcation. Now let me contrast that with the next one, which is the infinite period bifurcation that I referred to as a sniper in a previous lecture. So let's look at it in some detail now. There's 2 kinds of infinite period bifurcations, so this is one of them. Sniper for saddle node infinite period bifurcation. Or you can think of it as a saddle node bifurcation. Well, let's see. So just in terms of the jargon, saddle node infinite period. So that's S N I P E R, sniper. saddle node infinite period bifurcation occurring on the cycle. And so what it looks like, here's an example. Let's suppose in the radial direction we just have something like r dot is r times 1 minus r squared. That's a little system we've studied before, which we know drives trajectories to a radius of 1, except unless they start at the origin and they stay there. And theta dot will use a system that I think we've talked about before, maybe not. Maybe not, because I think we skipped the discussion of vector fields on the circle. But hopefully you read that here's a nice simple flow on the circle. Theta dot is omega minus sine theta, another first order system. Should we briefly talk about that? Maybe it's worth saying something, because we did skip that chapter. Let's quickly look at that. So theta dot versus theta for such a system, well, we just graph omega minus sine theta, and we have two kinds of pictures. Let's suppose omega is positive for simplicity. And if omega is pretty large, like say if it's larger than 1, the reason that 1 is important is because 1 is the amplitude of sine theta. And so if omega is larger than 1, then theta dot will never be 0. We'll just have a picture that looks, you know, like this. That's omega minus sine theta. Where this min is, I haven't drawn it very well. That's supposed to be a sine wave. But anyway, the lowest point would occur at theta equals pi over 2 when we're subtracting the maximum that sine theta can be, which is 1. So what you would have then is a flow that's to the right, but notice that it's relatively slow here. Geez, my chalk is not really cooperating with me. Try that again. It's really the slowest here. That is, we're moving to the right everywhere, but we're going pretty fast here. We're underneath a big high maximum in theta dot. So we're zipping around at, well, let's see, where would that be? So that's when we're subtracting negative 1. That is to say, this is at 3 pi over 2. So at a diametrically opposite point on the circle, that is, if we think of the flow actually on the circle, we're slow up here and we're fast down here. So it's a non-uniform motion. Like if you want to do it with your arm, it would look something like, you know, medium speed, then creaking, slow, and then whoosh, fast through there, and then slow again at the top. So it's a very non-uniform oscillation. And then notice that as omega gets closer to 1, this minimum is going to dip down, and well, at omega equals 1, it will touch the axis, theta axis, tangentially. And so that's the bifurcation we're interested in. That is, so this was the picture for omega greater than 1. And actually, while we're at it, let's just draw the whole phase portrait for the system. In the radial direction, we just go out to a radius of 1. So there isn't much to say here. We just have an unstable point at the origin. Our omega is greater than 1, so our theta dot is positive. We just increase theta monotonically as we're increasing our r. And so we spiral out to this non-uniform limit cycle that has a fast section and a slow section. And likewise, from the outside, we would spiral in onto the cycle. So there's a nice limit cycle existing when omega is greater than 1, but something bad is going to happen to it as we decrease omega. Now, what is going to happen? We're going to destroy that limit cycle through this process. Now, what's going to happen? Well, as omega approaches 1, the slow place is going to become so slow, and the period is going to be approaching infinity, that at omega equals 1, it's no longer a cycle. It'll be something else. So let's look at that picture. So then at omega equals 1, drawing our theta dot picture, we now have something like so, where we now have this saddle node bifurcation occurring in the theta dot dynamics. And so you see what's just happened, that we've now created this half-stable point up here at what used to be the slow point is now so slow that it's an equilibrium point. So on the circle, we now have this funny object, which you see why it's called saddle node bifurcation on the cycle, because a fixed point has just popped into existence on the cycle. And on the cycle, we're flowing this way and again this way, and we're fast down here. But we get stuck. That's actually a kind of homoclinic point, right? Because this orbit is leaving this fixed point, and then it comes back to the same fixed point. So that's a homoclinic orbit to a saddle node point. But then also notice that when omega is 1, we have an invariant line when theta equals pi over 2. So there's actually a whole line here that connects, right, theta dot is 0 in this case. When theta equals pi over 2 and r equals anything. So we have this invariant line that takes us from the origin to that odd point. That's also true coming from the outside as well. And then the remaining trajectories you can kind of get by just thinking about them. They have to look sort of like this. You know, they're going to approach r equals 1 from the inside and the outside. So there's that, and then in here we would go sort of like this, and then be running around on the cycle. And if we start pretty close by, we might go over like this. So, and also from the outside, we're just coming in. So anyway, that's the saddle node bifurcation on the cycle, the sniper. And then after the sniper has occurred, well, then you'd have in the theta dot versus theta picture, so when omega is less than 1, now you have something like that, which intersects the axis in 2 points. And so here we're positive, but here negative. We're actually flowing backwards on the circle, creating this stable point here, and then an unstable point there. So those will show up as rays, invariant rays in this circle picture. That is, there would be one ray coming like that, and then another ray like that. Where, let's see, the ray which is closer to 0 theta is the one that's going to correspond to a stable point, so we can put that in as stable. This one is the unstable one, so we're going this way. And on the cycle, the flow is like that. Both have radially outward trajectories coming to them on those invariant lines. And the same thing from the outside, those lines come in. And so then fill in the rest of it. You'd have, so now you see you have a saddle point here, drives trajectories over like that, or you can go around the long way this way. And then in here it's pretty confusing. I don't know. I mean, I guess you would sort of come out, well, what? I mean, maybe over here we go zoop, over into this point. And then everybody has to go there eventually. So, I don't know. Not going to really commit. Something like that, maybe. So everything ends up at that one point. And so depending on how you look at the series of transitions, you could say we've got a limit cycle. I mean, that's been our point of view. How can you destroy a limit cycle? One way is by making a slow point on it that then becomes an infinite period point. Now you're stuck, and then that can split apart like this. Notice you still have an invariant cycle. That is to say, if you're on the unit circle, you would stay there forever. But in fact, you'll just end up going either to this point, or if you started there, you'd stay there. So is there any question about this peculiar scenario? Let me talk about the scaling aspects of it now. We could again ask what happens to the period as we approach the bifurcation, and also what happens to the amplitude. And I want to draw a different picture also. Actually, maybe I should draw the picture first and then do the scaling. Right now, I would guess that for many of you it seems kind of abstract what we're talking about, like what does this have to do with anything? But I think the next picture will very much suggest something that it has to do with. Let's look at, instead of r and theta, let's look at x versus time. So, right, I mean, we haven't talked about the Cartesian coordinates x and y, but we could. They're implicit in these pictures. And so suppose we look at this diagram up here with the fast and slow regions on the circle. And so now think about x, that is x, just the sideways variable x, going this way. Here's the x-axis. Here's x equals 0. The picture should be centered at the origin. The axis should be up here, but I don't want to draw it there because I don't want to get in the way of the motion. So let's see what happens. Let's try to draw x as a function of time, starting, say, I don't know. How about right here, due east? Is that reasonable? I don't know. So what's going to happen? My x is going to decrease quickly until it gets to here. Then it's going to stay near 0. Right, it started at some max. This is actually the maximum of x. So here I am at some max, and I'm going to go following the flow quickly to an x close to 0. So I'll go something like this. Bzz. There, now my x is close to 0. Then I'm making that creaky sound, and I'm taking a long time to get through x equals 0. At first I'm on the positive side, and then I kind of grind through, and then I'm on the negative side. So that would look like this. Okay, now I'm on the negative side. Okay, once I get on the negative side, then whoosh, you go whoosh, all the way back to here. So what's that going to look like? Well, I was on the negative side. Then I go very negative. I go down to here, the most negative I can be, which is this place. So like an x of, say this is 1 and this is negative 1, that we've chosen the scale like that. So we would go down there. Then we quickly, just as quickly, go around through negative, through 0, through positive, and get stuck again. I won't make the sound effect anymore. But we would go up to, well, actually, it's more dramatic than that, right? I mean, this is really fast. So it should look sort of like this. And then very slowly through here, and so on. Did I do that wrong?
We're back to the bottom of the circle, right? So when we're approaching that
Got to go all the way back to 1. Right. Thank you. That's right. Good. Thank you. Good. Right. We go all the way back to 1. And then like that. Is that right? Yeah, that looks better now. Okay, so let's look at this again. Now, watch this again. So suppose you saw this on a monitor. Slow down, up, fast, slow. Does that look like anything to you? What? Looks like a pulse. Looks like the EKG. Right? That looks like a heart rhythm. And it's not an accident that if you study models of cardiac dynamics, you will find this kind of bifurcation occurring in models of nerve cells or heart cells. So this is really quite an important bifurcation for that reason. So this looks like a heart cell or a nerve cell firing. Well, heartbeat, really, as you said, pulse. The electrical part of the pulse, the EKG, electrocardiogram, typical picture. So it looks like sort of a heartbeat or a nerve cell action potential. And as I say, it's not just a qualitative resemblance. It really does occur in many types of models of nerves and heart cells. Okay. And so that was the picture I wanted to mention. But now back to the scaling. The question was, what's this period? That is, I didn't really emphasize how long this is, but it was meant to suggest that there's these two time scales. There's this slow time scale here, where that takes a much longer time than this amount of time, sort of the duration of the spike. And so we want to contrast those. So what is the period? It turns out we can calculate the period for this thing. Let's suppose we're still in this regime where omega is greater than 1, so we really do have a cycle. So the period t would be, we'd have to integrate dt from 0 to big T. And dt can be written in terms of theta dot by going d theta over omega minus sine theta. Because you can, I mean, theta, I've just solved for theta dot and then written it dt this way using that. And so that goes around once, so theta would go, say, from 0 to 2 pi. And that's a nice integral that you can do, depending how you were taught. You can do this with complex variables methods, with the residue theorem. Oh, some big ahs from the front row. You guys took complex analysis, or you're taking it now. Methods? Methods? Mathematical physics. Okay, whatever. So you can learn about complex analysis and residue theory there. But if you have not taken it, don't despair, because you might know how to do it another way with a certain trig substitution. Not many people know it anymore, and very few Americans, actually. I have found that our friends from Asia often know how to do this, but our friends from the US do not. However, please prove me wrong, some American. Do not prove me wrong, some Asian. I don't know. Anyway, there's a certain substitution with being American, of course, I can't remember it. It's either tangent, x equals tangent of theta over 2, or maybe it's arctangent. It's one of those. What? Does anyone remember it? There's an arctan. I think it's an arctan I want. No, don't look anything up. That's not going to do it in here. I'm not going to do the integral for you. But there's a certain trick which lets you convert trigonometric expressions into rational functions. And that trick involves, I think it's got to be an arctangent. Let's see. I do have notes. Does it say here? That's equivalent to looking it up. I know it's cheating. No, I don't have it. Okay. Anyway, that could be an exercise. Figure that out if you want. But anyway, whatever. So using either this mysterious trig substitution or residues, you can compute that this integral is 2 pi over square root of omega squared minus 1. It's a nice definite integral. So that's a nice formula. Notice it works right in the limit. Suppose omega gets very large, much larger than 1. Then this behaves like d theta over omega, which would have an integral of just 2 pi over omega. So this is approaching that for large omega. But the interesting thing is that this is singular when omega is 1. That is, if we factor it, you see it's 2 pi over square root of omega plus 1 times square root of omega minus 1. And so this, is approaching 2 pi over the square root of 2 times this singular object, 1 over the square root of omega minus 1. That is, this is blowing up to infinity at a particular rate, like 1 over a square root of 0, so to speak. So this turns out to be a universal thing. Near one of these saddle node bifurcations on a cycle, you always find, I'm not proving that, but there is an argument in the book. If you want, read the section about ghosts and bottlenecks. There's a very generic argument that shows that the period near this will always increase like 1 over the square root of mu. I mean, where there's a constant, like this constant. But ignoring that, the divergent part is always 1 over a square root, where the mu, in this case, would be omega minus 1. But in the general case, mu is the distance from the saddle node bifurcation in parameter space. So I won't show you that, but that was the scaling that I wanted to mention, that it blows up, the period becomes infinite in a particular way, like 1 over square root of x, as x goes to 0. So back to then, what about the amplitude? Notice that the amplitude of the cycle is still order 1 the whole time. The cycle is not getting smaller. It's only that the period is getting longer. So the amplitude stays order 1 as mu goes to the critical case, which I guess I've set it so that mu equals 0. Okay, so those are our scalings there. And let me summarize what we have then. By the way, in my nationalistic remarks, I didn't say anything about Europe or Africa or South America. I'm sure those people can all do these integrals too. Sorry to leave out the rest. Or Antarctica. Any folks here from Antarctica? But okay, now back to the table though. So the universal behavior that I wanted to just list so this is universal near bifurcations of cycles. So again, I'm going to sort of let mu equal the distance from the bifurcation in the sense that I just tried to describe in parameter space, where I think of mu as some quantity very small, so that as I'm close to the bifurcation. So mu equals 0 is where the bifurcation occurs. Then we could ask what's the amplitude of the stable cycle when it exists after it's created or before it's destroyed, however you want to look at it, and the period of the cycle, again, near the bifurcation. And so then we have these different phenomena depending on whether we have a supercritical Hopf or the saddle node of cycles, or the sniper. So these sort of sound like the same thing, but remember they're not. One is the two cycles coming together and annihilating. The sniper is the creation of a saddle node fixed point on the cycle. And then the last one is one that I haven't discussed yet, which I'll call a homoclinic bifurcation. And I'm not planning to discuss it today, possibly at the end of the course, but I would like to just kind of plow through this material, so I'm going to leave that. If you do want to read about the homoclinic, it's discussed a little bit in section 8.4, and then there's a nice physical example of it in section 8.5, where I talk about the bifurcations that occur in a whirling pendulum that's been driven by a constant torque. Or there's also a superconducting version of it called the Josephson junction, which if you like applied physics or want to learn about superconductivity, you can read about the dynamics of a Josephson junction, which obeys the same rule as the same differential equation as a forced pendulum. So that's discussed in section 8.5, and maybe we'll get to that at another point. But anyway, just for now, to summarize, the things we've already seen are that when at a supercritical Hopf, the limit cycle is born small. Its amplitude is only square root of mu. So it's a tiny limit cycle. It has emerged from a point. But its period is order 1. So it's oscillating perfectly well. It's just tiny. Whereas when we have the saddle node bifurcation of cycles, they're big and they're moving at a brisk pace. So they're order 1 in both their amplitude and their period. Sniper we just talked about. We've seen that its period goes to infinity like order mu to the minus a half. That is 1 over square root of mu. But its amplitude is not affected much at the bifurcation. It's just order 1. And finally, the homoclinic that I haven't discussed, but which involves a limit cycle getting close to a saddle point and then touching the saddle point at the bifurcation. There, the amplitude remains order 1 when the cycle exists and is stable, but its period goes to infinity, but in a different way now. Its period goes like, so this is large, of course, a large period approaching infinity. And this is also large, but it's a different scaling. It goes like the absolute value of the natural log of the distance from the bifurcation. So order of absolute log of mu. So I mention this because sometimes in experiments you don't have a good model of the system. You just have observations. And you can sometimes tell by making careful measurements near a bifurcation, like if you have a stable, you have a periodic behavior in your experiment, and then it disappears. By using this table, you can sometimes make a good guess about what the bifurcation is that killed your cycle. And it'll be one of these 4 cases very typically. That's what I mean by universal. I don't mean that nothing else could happen, but these are the very most common situations. And so this kind of information will constrain a model. I mean, if it obeys certain scaling laws, then if a model is right, it's got to have this type of bifurcation in it. So I think I'll leave that discussion there for now. Is there any question before we move on? Okay. So that's section 8.4 for now. Let me jump to section 8.6. As I say, 8.5 is interesting, but it's a complicated and fairly long section that I don't want to do right now. But 8.6 is quick, and let me just show you that, because it has a few little surprises, some new phenomena that we really haven't thought about at all. So 8.6 is about coupled oscillators, where I'll show you a bifurcation that is one of these that we already discussed, so not new. But the new wrinkle is that we'll also see a phenomenon called quasiperiodicity. And quasiperiodicity is something that does not occur in any of the phase spaces we studied so far. We had been looking on the plane mostly. We also talked about the line and the circle. And we did a little bit on the cylinder in the case of the pendulum. But, you know, if you think about two-dimensional spaces, for two-dimensional phase spaces, what are the possibilities? Let's suppose we stick to orientable surfaces, so we're not going to use Mobius strip or projective plane or a Klein bottle. I haven't seen much use for those in science. I guess conceivably they could be useful in some settings. But the really common ones are, well, the plane, which we've been discussing, cylinder, where we have one variable that represents an angle and one that represents a real number. We saw that in connection with the pendulum, where the angle variable was the angle of the pendulum and the real number was the velocity. Then we could also study a sphere, but nothing much really new happens there. So I'll just sort of say it's like the plane. That is, there's no really qualitatively new phenomena that happen on the sphere. But the torus does bring up a bunch of new stuff. And so that's what I want to discuss now. So a torus would be the case that would come up if we had two angles. Like suppose I have a system theta 1 dot is some function of theta 1 and theta 2, and theta 2 dot is also a function of theta 1 and theta 2, but a different function. And so the torus is very natural for problems that look like this, where you have two angles. And in settings like this, these f's will be 2 pi periodic functions of their arguments. 2 pi periodic in both arguments, which is why it's natural to think of these as angles. That is, when you go around 2 pi, you're at the same state, because the f's are periodic. So now, how to think about a torus? There are various ways of visualizing it. One way that is sometimes helpful is rather than thinking about a torus, just think about a circle. That is, we have two thetas. So you could just say, well, here's a theta. And then here's a theta. And, you know, you could, if you want, think of them as angles relative to east, like that. But, OK. So we have these thetas, and then as time evolves, they move around on the circle. So I like to think of it as two runners that are running around on a track, circular track. And that's OK. But that's not really our phase space picture, because we have 2 points. Whereas in phase space, the whole point of phase space is that we just have one point that represents the state of the system. And so in a phase space way of looking at things, you'd have a single point on a torus with coordinates theta 1 and theta 2. So that picture can be interchanged with this picture. That is, OK, how to draw a torus. One way that people often do is like this, and they put a little pair of lines like that. That's supposed to look sort of like a perspective drawing of a torus or a donut, a bagel, whatever your favorite food is, a lifesaver. OK. And so then theta 1 might represent this angle going around, which is kind of analogous to longitude on the Earth, and the other would be like latitude, which would be an angle that harder to draw, but sort of goes, if you'll forgive me, it goes around like this into the hole of the torus, comes out the bottom, goes around like that. That's the theta 2. Right? You see what I'm trying to indicate? So there's the one that goes around. Well, whatever. Hopefully you know what I'm saying. Okay. So you have those two angles. Now that's a little awkward to draw, but anyway, we have these trajectories moving around on the torus, and this other way of drawing that's easier will be familiar to you, especially if you played video games or other games on the computer, where when you go off the edge of the world, you reappear on the other edge of the world. I love those games. Like there's somewhere you crash, you're flying some kind of airplane, you crash, but hey, I'm not dead because I've come back alive up here. Yeah, asteroids? Yeah. Okay, and then you can also go off the edge of the Earth this way, and you'll reappear amazingly over here. Yeah. Okay, so that picture of a square with periodic boundary conditions also works. So then that's probably the easiest way to draw the torus. Just draw it as a square, but make 0 and 2 pi be equivalent as far as, that you just, like I say, just after you go over 2 pi, you pop back at 0. Okay, so we'll use that picture frequently. Now, you might think there isn't much to say about the simplest conceivable system, but I want to start with the simplest conceivable system, which is just theta 1 dot equals omega 1, and theta 2 dot is omega 2. Really pretty absurdly simple. Just constant numbers. So we know what the trajectories are. We can just integrate this. Omega 1t plus a constant and omega 2t plus a constant are the thetas. So we'll move in straight lines on the square. Actually, let me think of this as a special case of a little more general system. I mentioned that I want to talk about coupled oscillators. So in a moment, I want to discuss this system. Theta 1 dot is omega 1 plus a coupling between theta 1 and theta 2 given by this. A constant times sine theta 1 minus theta 2. Sine theta 2 minus theta 1. And also, theta 2 dot is omega 2 plus that same coupling constant, sine theta 1 minus theta 2. So this is, I'm doing first the special case where the k's are 0. But this system I will want to get to momentarily. Okay, but first we're doing this very trivial looking case of no coupling. Just independent, think of them as independent runners on a track. And it's sort of like people who don't know each other, they don't slow down when they pass each other, they're not talking, they don't hate each other, they're not running away from each other, they're just running. Okay, so they ignore each other. And then on the square, you'd have straight lines. So this is the case of the k's equals 0. And so a trajectory will look like so. You just, depending on the ratio of omega 1 and omega 2, so let's see, we're calling this one theta 2, this is theta 1. We go up with some slope, follow a straight line, we'll go off the edge, and then you have to draw a dotted line to the place where you would reappear, and then continue with that slope. Draw a dotted line. Again, the same slope. Now we've gone off this edge. So now we have to draw a sideways dotted line. Oh, that's interesting. So I almost look like I came back to my starting point. So that is possible, right? I mean, you could have it so that you'll repeat. That's conceivable. You'd also have to be very lucky to get that to work out. I mean, it could be that you don't quite hit your starting point, And then you have a picture where, like, maybe suppose I had landed just slightly above, then my new trajectory would be like that, and then down here, and so on. So these are the two cases I want to talk about. Do I close, that is, do I land at my starting point after a certain amount of this, or not? And so those are two cases that we have to talk about. Case one, can you tell what determines which case we're in? Does anyone see? How do I know when I'm going to have a closed orbit or not in this picture? Go ahead, yes? The ratio of the omegas will control that. And what do I need to know about the ratio? Whether it's what? Whether or not it's a rational number. Is it a ratio of two integers? Right? Like suppose it's, that is, if it's a rational number, then we will form closed orbits. So let's look at that case. Suppose omega 1 over omega 2 is of the form p over q for some integers p and q. So we have a rational slope. Then, and for simplicity, let's suppose that p and q have no common factors. If they do, just divide them out. So they're relatively prime. And then this will cause a closed curve to appear on the torus from any initial condition, actually. So the torus would be filled with closed curves. Closed, that is to say, periodic orbits. And we know a little bit more about them, which is that if the ratio is, as we say, p over q, it means that we're going to go p times around the one circle in the same time that we go q times around the other circle. Or if you want to think of it as runners, if one runner is 5 times faster than the other, let's say, that runner will make 5 laps in the time that the other one makes 1 lap. Or if it was 3 to 2, then 3 laps for 2 laps. So now let's look at that case of 3 to 2, actually. That's interesting. So the idea, though, is that theta 1 does, in this case, p revolutions, or laps, in the same time that theta 2 does q laps. Maybe I'll come over here since I have some extra space. Now, I mentioned p equals 3 and q equals 2 as an interesting case. It's interesting because something that we have not seen before can happen. All our closed orbits in the course so far have lived in the plane or on the cylinder. But now that we're on the torus, you could kind of think of the torus as living in a 3-dimensional space, like a real donut does, or an inner tube of a tire. And if you take this case, p equals 3 and q equals 2, the closed orbit visualized in 3-dimensional space will have a knot tied in it. So you may have wondered, can limit cycles have knots? Yes, they can. Here's an example. These aren't limit cycles. These are not isolated closed orbits. But still, you can have closed orbits with knots in them. This gives the closed orbits in this case are what in knot theory are called trefoil knots. So a trefoil knot is the simplest knot. It's similar to the knot you would make in your shoelaces if you then glued the tips of your shoelaces together. So it looks like this. This is how it's often drawn. Some people call it a clover leaf knot. Let's see here. So it's a little tricky to do these knots. Got to go over here. And this is under. That's over. There. So that's a trefoil knot. And now what does that have to do with our torus? Maybe you can see it. That is, draw the torus from the top view. There's a hole in the middle of the torus. And now imagine what it would have to look like if we go 3 times around one of the circles while going 2 around the other. You can see that there's a trajectory that goes sort of like this. I'm on the top of the torus now. Then I dive into the hole. Now, when I'm on the bottom of the torus, I'll continue to rotate, and I come out over there. Now I'm visible again on the edge of the torus and now on the top. I'll come around, go into the hole again. Now I'm underneath, and continuing to rotate. I got to go something like, no promise that this is going to work out right. I'm underneath, resurface on the top, going this way. And what else? I have to dive one more time into the hole, once more into the breach, underneath, coming around, and then reconnect over there. Well, that's a pretty lopsided looking trefoil. Can you see that I've tried to draw? Well, it's a little bit tilty, right? This thing's, that's the beauty in topology. It's allowed to be tilted. So I'm off, kind of, but you get the idea. Okay, if I want to draw it a little more accurately, maybe it should be a little more symmetrical looking. This would have to be about like so, and then something like that. That's not too great either, but okay. Anyway, what was my point? That I've got this closed curve that's got a knot tied in it in 3 dimensions. Okay, maybe you don't care about that. But I think that's pretty cool. And this will occur whenever P and Q are relatively prime. It's not anything special about 3 and 2. So these are called torus knots for obvious reasons when you have P and Q relatively prime. Is there any question about what I just showed there? Okay, so that can occur even, yes?
They're not all necessarily trefoils, right?
No, they're not trefoils. What I'm trying to say is that the generalization when they're P and Q is then they're called PQ torus knots. So the trefoil is the special case 3 to 2. But you know, if you had 5 to 3 or 11 to 8 or whatever, those are all different kinds of knots. Yes? Relatively prime, no common divisors. So they're not prime numbers. Like 8 to 3, 8 is not a prime number. But 8 and 3 don't have any factors in common. So that will still make a knot. But if they do have factors in common, like 4 to 2, that's not going to be a knot, I don't think. Yes?
Isn't there always cases to make it so that you reduce it so that it's always relatively prime? The ratio is the same.
Well, I also don't want to do a case like 5 to 1. So I want P and Q. So I'm just trying to be a little bit careful. Yeah. So something like 5 to 1 just looks like a spring, you know. But yeah, you're right. Otherwise, you can make them relatively prime. So this is a very common phenomenon in that sense. Okay. But on the other hand, rational numbers are themselves not a common phenomenon. Right? You may have learned in some other course that if you look at real numbers, almost all real numbers are irrational. The rational ones are very exceptional. They have measure 0 would be one way to say it, or they're also countable. So there's 2 different ways in which the rationals are very small. If you haven't run into these ideas of countable, uncountable, or measure, don't worry about that. We'll talk about that a little more when we get to fractals. So having said that, let's talk about the irrational slope case, because that's where something really new can happen. I mean, yes, okay, we have these periodic orbits with knots tied in them, but something really even stranger is this case 2, where suppose the omegas are not going to create a rational ratio. If omega 1 over omega 2 is irrational, like say omega 1 is the square root of 2 and omega 2 is 1, or something like that, then we get quasiperiodicity. And so what that would mean is, I can't draw it really, but I'll just try to indicate it. This is the case where, you know, you're going up, but you don't ever close. You just keep going. And so if you just keep drawing this picture over and over, the lines will never touch each other. They'll just keep going and going and going, and they never close. Which might sound to you, okay, so there's a tendency in physics to say it a certain way, which I don't like, which is that sometimes they'll say that a quasi-periodic trajectory goes through every point on the torus. That's not actually true. It does not do that. It doesn't go through every point on the torus, but it is dense on the torus. So that's the official way to say it in math. That is, every trajectory on the torus does not close so how do we know it doesn't close? If it closed, that would mean that we could count the revolutions. It would have gone would have gone some integer number of revolutions around each circle, and you'd be back in the P over Q case. So it can't close. So given that, and every trajectory does not close, and every trajectory is dense on the torus. By that I mean that you could do this little test. Pick your favorite point on the trajectory, or pick your favorite point on the torus, anywhere. Okay, like this point has not currently been hit. Will that point eventually be hit by a trajectory? No, not necessarily. However, if I draw an epsilon disk around that point, where epsilon can be as small as I want, as long as it's not 0, the claim is that the trajectory will penetrate that epsilon disk eventually. Okay, that's the statement. That the trajectory gets arbitrarily close to every point, but it doesn't necessarily hit every point. It gets epsilon close to every point, where epsilon is as small as you want. So that's the statement. So in that loose sense, you could say the trajectory goes everywhere. It certainly comes close to everywhere, but it doesn't literally go everywhere. So it's kind of amazing that this thing can just keep going. I mean, why is it amazing? To me, it's amazing that a trajectory can live on a compact set, like a torus, a closed set, and keep going forever and ever, and yet never cross itself. It doesn't seem like there's enough room for that, but there is. And that's what it does. Now, you could ask, is that chaos? It's not chaos. It's a milder, it's still weird, but chaos is weirder than this. And I'll explain why later, but that's, you have a question.
So what's the reasoning why you can't ever, there's no reason why you would never...
How do I know it doesn't close? Or how do I know it's dense? Yeah, how do I know it's dense? I might want to give you a homework question about that. I'm not sure I want to say something about that. I think if you try to think about it, it's a good exercise. Yeah. So let me not give you any ideas about that. Was there another question? Okay. So I said, of course, I haven't said what chaos is yet, so it's meaningless for me to say this is not chaos. But the key thing that's, I'll just give you a little foreshadowing of what we're going to discuss. Suppose you compare two neighboring points, like say this point and one on a trajectory near it. And think of them as sort of like buddies, and they're running along on the torus. You want to ask how far apart are they as time goes on? do they diverge from each other exponentially fast? In a chaotic system, they would. That is, nearby states get exponentially separated, at least at short times. They can't exponentially separate forever and live on a closed, bounded space like a torus, because they can't get farther apart than the diameter of the torus. But when they're close initially, in a chaotic system, there's exponential divergence. Whereas here, you could check just by exactly calculating theta 1 and theta 2 of t. They're linear in time. So the distance between these two, while it will grow, it will grow linearly in time, approximately. It does not grow exponentially fast. So nearby trajectories don't separate very fast in a quasi-periodic system. And for that reason, they're not considered chaotic. Where do these come up? They come up all over the place in classical mechanics. So it's very common to see them. I guess I just wanted to say one thing about the coupled oscillator case, and then we'll stop. So back to the coupled case. Let's look at that for a second. I have the equations up there on the top board. And so if I introduce a variable phi to try to understand what's going to happen in my coupled oscillator case, it's natural to look at theta 1 minus theta 2 because our equations, which remember looked like this, theta 2 dot is omega 2 plus k sine theta 1 minus theta 2. Both equations in the sine function, they only depend on the difference of the angles. And what this means is, like in terms of the runners, that there's coupling between them in the sense that if theta 2 is a little bit ahead of theta 1 on the circle, and let's think of k as being a positive number, then if this is a small angle difference, this will be sine of a small positive number, which will be positive, times k, which will be positive. So what's going to happen is we're adding a positive number to omega 1. And so it means in a situation like this, where they're both running this way, the runner who's behind will get a positive term added to his or her speed, meaning the person behind will speed up. And the person ahead will slow down by this amount. So it's a coupling that tends to synchronize the oscillators, the runners. It tends to pull them together in phase. And that's something you would want if you're running with your friend who's a slowpoke. You want that person to speed up. Come on, catch up with me. And you might slow yourself down so that you can stay together and talk. Anyways, that's what this model is about. It arises in other settings, but let's not discuss that now. Anyway, so with this phi, we're looking at this angle between them. Phi would represent that angle. And by subtracting the equations, you can see phi dot would be, well, let's see. So it's omega 1 minus omega 2. And then we have, it looks like minus 2k sine phi. And you might recognize that because that's the equation, well, with different letters, that we discussed earlier when we were talking about the infinite period bifurcation, the sniper. So the same analysis will apply. And what we can see is that when omega 1 minus omega 2 in magnitude is less than 2k, then we have, we'll have two fixed points on the phi star will have two fixed points. Sorry, there's two fixed point solutions. What am I trying to say? Two fixed points for phi star. And so the diagram on the torus would look like this. Lines where phi is constant in this picture, phi equals constant would mean theta 1 minus theta 2 is a constant. And that will mean that we're moving on a diagonal line. So we would have a picture like this. Diagonal line with a slope of 1. And then we'll also have another diagonal line, which is going to turn out to correspond to the unstable phi star. That is, when I say there's two of these fixed points, one will be stable, one will be unstable. And you can check that they're going to look about like this. And that the flow takes you onto this curve away from these curves. So what I'm saying is that in this system where the k is sufficiently large in the sense that I just wrote down, 2k greater than the difference in the frequencies, that the system will end up running on this kind of a diagonal line, which corresponds to what's called phase locking. That is, the phases will be locked together with phi1 minus phi2 equals some stable distance. That is, the runners will be synchronized. They're not going to run side by side, but they will keep a fixed distance between them asymptotically. And if omega is, not in this regime, then they won't be able to run together. One will continually lap the other. All right, thank you. I think I'll stop there.